In this video, I will be discussing two-dimensional collisions. So far, we have studied up until this point just collisions that are in one dimension. However, most collisions in real life are not restricted to one head-on collision where the objects move in a straight line. In two-dimensional or even three-dimensional collision of two or more particles, we can apply the same methods that we have applied before for conservation of momentum and also conservation of kinetic energy if we're dealing with elastic collisions. However, now we need to remember that momentum is a vector, so it has both magnitude and direction. So hence, when we talk about momentum being conserved, we need to be careful and say that it's momentum being conserved vectorially. So let me just go to a little bit of an animation to kind of show you a collision. So imagine you're playing a game of pool and you have this green ball over here that's off center from the red ball over here. And I'm just going to press play and show you the animation as it moves along here. So there's the red ball coming along and I can see the tracing of the path. And then here's the rebound of the two objects afterwards. I'll just pause it right here and you can see that they have two different velocities and they also have an angle that they make with respect to the original line that the red ball came in at. So as we did before, you would draw a before or initially picture and a finally picture of the two balls as they are rebounding off of one another. Now it would be good to choose an appropriate coordinate system, and I usually like to pick one of the balls, say this ball M1 which is moving along here. I'll choose this to be the x-axis. And then the other ball here, the red one in this picture, is initially at a velocity of 0. The next thing I would do is write down all of the known information, such as the masses M1 and M2, both in the initial and final pictures. Then we have the initial velocity V1 initial here. V2 initial here is assumed to be 0 in our setup here. And then we also have the final velocities V1 final and V2 final. And don't forget, we also have the angles. I'm going to label this as theta 1. And over here, I'll label that as theta 2. And this is continuing to move in a straight line, so this is also theta 1 that is made with respect to the velocity and the x-axis, and over here is theta 2. And the next step, what I would do is, since momentum is conserved along all of the directions, and we're looking at a two-dimensional collision here, then we're going to be applying conservation of momentum along the x-axis and along the y-axis. This velocity needs to be broken up into components. So V1 and V2 need to be broken up into components in the afterward pictures. So you want to write down the expressions for the x and y components of the velocity vectors. Each velocity, for example V1 final, should be broken up into two components. I'm going to label this as V1 final along the x-axis and V1 final along the y-axis. And over here, by the way, this is theta 1 as we had defined earlier in our diagram. And here's a picture showing all the velocities now in a nice right triangle. So therefore I can use trig ratios. For example, the sine of theta 1 would be equal to V1 final along the y-axis divided by V1 final. So V1 final on the y-axis is V1 final times sine theta 1. We could also say cosine theta 1 is equal to V1 final along the x-axis divided by V1 final. And so we have V1 final along the x-axis equal to V1 final times the cosine of theta 1. And so therefore we've expressed the velocities in their component form. We can do a similar thing for the ball number 2, and we would get V2 final x will be equal to V2 final times the cosine of theta 2. And V2 final along the y-axis will be V2 final times the sine of theta 2. However, notice that the velocity for V2 final here is going in the negative y-axis. So you need to be careful. There's V1, V2 final along the x-axis, but V2 final on the y-axis is going downwards. So this is really negative. So be careful with signs. So there's the velocities for the x and y components of the second ball. By the way, if you look over here initially, you could do the same thing as well as if you had say a ball coming in at this angle, another one coming that way, and then they go off at different angles. You could do the same situation. Turns out here, just because we chose a really convenient coordinate system, that v1 initially in the x direction is really just v1 initially, and v1 initially in the y-axis is 0 because there's no initial vertical velocity. We chose to set the coordinate system right along our velocity of the first ball. Now v2 initially in the x and v2 initially in the y are both 0 because this ball is really at rest. Okay, so we've drawn our initial and our final pictures. We've labeled all the given information, and we wrote down all of the expressions for the velocity vectors in the x and y directions for each vector. Now we're ready to apply the conservation of momentum along the both axes that are given. So remember that momentum is a vector, and so we're going to be using conservation of momentum along the x and y-axes. So to indicate that you're conserving momentum along the x-axis, we write momentum initially in the x direction, you could write x and then a comma I, or you could write I and then comma x, doesn't really matter, is equal to the momentum x in the x-axis along that is final, for the final picture. So start off with this, because this is stating that you're assuming that momenta of the two objects before is equal to the sum of the momenta of the two objects afterwards along the x-axis. So now then you could write the next line here, and you're summing all of the momentum along the x-axis. So for the first ball, you would have something like m1 v1 initially in the x direction plus m2 v2 initially along the x-axis, and then finally m1 v1 finally in the x direction, and then m2 v2 finally in the x direction. You can see there's a lot of subscripts, but I think it's important to show all these subscripts so that you don't get messed up with it. Now, by the way, if this was a game in which the two balls had the same mass, then you could cancel all these masses, and that would make life a little bit easier for you. Okay, in this particular example, you can see that the second ball is at rest, so this term will drop out. And then you can replace this v1 final x with v1 final sine theta 1, and this v2 final x with v2 final cosine theta. And you're probably usually given all the information except for, say, two unknowns. And you might have two unknowns in this equation, and you'll probably have to move into the next equation for momentum along the y-axis. So it's a very similar equation. You're going to write the sum of the momenta of the two objects before along the y-axis is equal to the sum of the momenta of the two objects afterwards along the y-axis. So this will be written out more explicitly as m1 v1 initially along the y-axis plus m2 v2 initially along the y-axis equals m1 v1 finally along the y-axis plus m2 v2 finally along the y-axis. Now, in this particular example that I've shown here, you can see that the velocity initially in the y direction is 0 for both balls initially. This one is completely moving horizontal, so there's no vertical velocity, and this one's simply at rest. So if we move down to our equation here, this would actually cancel out to be 0. This would cancel out to be 0, so you would actually have a total momentum of 0 initially. And that means that these two terms are going to cancel out. And if you recall that we had a negative velocity here. So the momentum of the second ball, that term is going to be negative because of that negative velocity. And so this will be of equal magnitude of that, but it'll be negative direction, right? And so they'll balance out to give you 0. Okay, so that gives you a typical problem to solve where you have to figure out two of the unknowns from these two equations. Now, one question that comes up often in questions like this is, how do we know whether this is an elastic or inelastic collision? Right? What's the test to tell whether this collision that you've just found out, and say you solve for some unknown velocities or angles, how do you know whether it's an elastic collision? If you recall, elastic collisions are the only type of collision where the kinetic energy totally is being conserved. That means that if you were to add the kinetic energy of the first ball, 1/2 m1 v1 initial squared, plus 1/2 m2 v2 initially squared, that sum should be equal to the sum of the kinetic energy afterwards. Now you notice when I'm writing this down, I'm using just the resultant speeds. That means I'm not using the x velocities or the y velocities. I'm only using the actual resultant speeds here, v1 final, v2 final, v1 initial, and v2 initial. I don't use components. Remember that energy is not a vector, right? So when you're applying conservation of energy, you only use the resultant velocity. So if the right side of this equation is equal indeed to the right side of that equation, then you know you have an elastic collision. Sometimes, if it was a really evil question, I suppose, we could possibly tell you that's an elastic collision and give you 3 different unknowns to find, and you have 3 equations and 3 unknowns. That would be kind of nasty algebraically, but that is possible. Furthermore, you could even have more equations than that. We could even apply this to conservation momentum along all 3 dimensions. Okay, I think you're ready now to practice using conservation momentum in 2 dimensions.